Hello my dear student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to talk on module Applications of Electrospun Nanofiber under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn applications of polymer nanofibers as reinforcement agent, application of polymer nanofiber for filtration as a catalyst, chemical and photocatalyst, humidity and gas sensor, use of polymer nanofiber in energy storage, energy generation devices such as lithium-ion battery, fuel cell, in biosensing and water treatment too. Let us discuss the application of electrospun nanofibers. With the development of electrospinning, diverse material has been successfully used in electrospinning for nanofibers, including organic material, organic inorganic material, and inorganic material, with the diameter ranging from microscale down to nanoscale. Additionally, the variety of architecture based on electrospun fiber has been realized, such as solidified fibers, porous surface pores for interior pores, fibers, hollow fibers, core cell fibers, hierarchical structure fibers, etc. These unique advantages of electrospinning afford the multifunctional properties for diverse application, including nanofiber reinforcement, filtration, catalysis, electronic devices, lithium-ion battery, fuel cell, biomedical field, etc. In this section, we will present the application of electrospun nanostructures in nanofiber reinforcement, filtration, catalyst, electronic devices, lithium-ion battery, fuel cell, biomedical field. The product of submicron as well as nanometer size fibrils by electrospinning was reported early in 20th century. Over the intervening decades, researcher has continued around the world, resulting in over 100 patents and publications. Researcher today continue to focus on new method of producing nanofibers, including an increased understanding of electrospinning and its application. These studies have resulted in process improvement that have increased the speed of electrospinning, increased the strength of resulting nanofiber wave, and may lead to better control of electrospun membrane features such as fiber size, fiber orientation, porosity, and for future application. I want to discuss the applications of electrospun nanofibers. Polymetric nanofiber, which is non-woven material produced by electrospinning, have extremely high surface to mass or surface to volume ratio and a porous structure with excellent pore interconnectivity. These characteristics plus the functionalities and surface chemistry of the polymer itself impart the nanofibers with desirable properties for a range of advanced applications. These applications may be in the field of environmental engineering and biotechnology as membranes and filters. The second, in the field of defense, security as chemical and biological protecting sensors. In the field of healthcare, for tissue engineering, tissue repair, and drug delivery. Electrospun nanofibers are potentially being used for solar cell and fuel cell as energy storage devices. Many more applications of electrospun fiber in the diverse field are possible due to the possibility of easy tailoring the properties of fiber as per need. I will discuss electrospun nanofiber as reinforcing agent. One of the important applications based on traditional fibers as microscale such as carbon fiber, glass fiber is to act as fiber reinforcement in composite systems. With the aid of these fiber reinforcement, the composite material exhibit superior structural properties including high modulus and strength to weight ratio. Prompted by these practical applications based on traditional fibers, electrospun nanofiber have been investigated in fiber reinforced as well, driven by their better mechanical property than bulk fibers. Several research papers has been published on the uses of electrospun nanofiber reinforced composites in dental restorative matrix. It has been also found that reinforcement of nanofibers is suitable to improve the interfacial adhesion between nanofiber, non-woven and dental methacrylate of BIS GMA TEGDMA. Natural electrospun nanofiber has also been investigated in nanofiber reinforced composite for biodegradable applications. Research have been explored potentialities of ultra-fine cellulose electrospun nanofiber as a reinforcing agent for polybutylene succinate (PBS) for biodegradable composite and electrospun cellulose nanofiber to reinforce polyvinyl alcohol PVA film for biodegradable composite. Composite laminate interleaved by nanofibrous mats at plies interfaces has been shown in the figure. It is believed that nanofiber, being characterized by a diameter typically in the range of few hundred nanometer, can be small enough to reinforce regions of the matrix located between adjacent plies of laminate as schematically illustrated in the figure. The idea of using nanofiber to reinforce small-scale places, such as the regions at the interfaces of laminated composites, arises from the consideration that in such composite, structure failures mainly occur in a small critical area, in particular in matrix-rich microvolume, where the matrix is not reinforced and is experiencing high stress concentration. Therefore, it has been proposed that the incorporation in laminate composite of an entangled nanofiber layer characterized by a combination of interlocked in-plane and out-of-plane nanofibers might contribute to improve the interlaminar fracture resistance, much like the hooks and loops in Velcro. I want to discuss the Electrospun Nanofiber filtration application. Filtration is one of the important fields of engineering. It was estimated that future filtration market would be up to US 700 billion by the year 2020. For high filtration efficiency, it is generally necessary that the size of the channel and pore in the filter material should match the scale for the particle or droplets that is to be captured in the filter. Taking the advantage of very high specific surface area, good interconnectivity of porous, low basis weight, high permeability, and controllable pore size of the electrospun nanofiber. Electrospun nanofiber non-woven have been widely used in air and liquid filter application. Usually, the particle filtration occurs via multiple collection mechanisms such as sieving, direct interception, interstitial impaction, diffusion, and electrostatic collection. Till now, many highly efficient nanofilters made by the nanofibers has been realized. For example, few researchers has demonstrated the high efficiency particulates air, which is known as HEPA filter based on nylon 6 electrospun nanofiber with the diameter 80 to 200 nanometer. Basis weight is around 10.75 gram per meter square, which exhibits minimum removal of efficiency of 99.97% of particles greater than or equal to 300 nanometer in diameter. Another report is available which suggests the separation of micro submicron polystyrene particle of the 0.5 to 16 and 10 lm from water based on electrospun nylon 6 nanofiber with a diameter 30 to 100 nanometer. As the diameter of the polystyrene particle is greater than or equal to 1 lm, the removal efficiency can be 100%. When the diameter of polystyrene is 0.5 lm, the removal efficiency is higher than 90%. It is well known that heating, ventilating, and air conditioning air filters usually opened in dark, damp, and ambient temperature condition, which is susceptible for bacterial, mold, and fungal attacks, resulting in unpredictable deterioration, bad odor. To solve this problem, functionalization of surface of filtering media with antibacterial agent for long-lasting duration, antimicrobacterial functionality is of the current interest. For example, antimicrobial activity of PUC after incubation for 24 hours, blank and PUC against Staphylococcus aureus and B1 black and B2 is for PUC agent E. coli has been shown in the figure. we're going to talk about electrospun nanofibers as chemical catalyst. It is well known that nanostructured material have opened new possibilities for creating and mastering nano objects for novel and advanced catalytic material. In general, catalyst is a molecular phenomena and the reaction occurs on an active site. A crucial step in catalyst is how to remove and recycle the catalyst after the reaction. The immobilization of catalyst in material with large surface area advance an interesting solution to this problem. Taking the large surface area and high porosities, electrospun nanofibers as a novel catalyst for support for catalyst have been widely investigated in catalyst field. Here I will discuss the application of electrospun as chemical catalyst. In 2004, the scientists demonstrated a simple in situ electrospinning route for directly depositing iron nanoparticle with different size on carbon nanofibers, which is shown in figure A. In this study, pan and iron acetonate were used as a precursor. Carbonization, hydrogen reduction were used to convert the precursor into iron-carbon composite fibers. With those iron nanoparticles as chemical catalyst, carbon nanotube can grow on the surface of carbon nanofibers with controllable length by supplying the hexane vapor with different time as shown in figure B. Let us discuss the electrospun nanofiber as a photocatalyst. Photocatalytic performances based on diverse electrospun ceramics of TiO2, ZNO, SNO2 and so on, nanostructured nanofibers and nanotubes has been carried out. With the development of the photocatalyst, scientists found the fast recombination rate of photo-generated electron-hole pair, which hinders this technique in practice. Coupling semiconductors of metal oxide with different band gap width is an effective route to enhance the photocatalytic activity by increasing the separation of photo-generated electron-hole pair and extending the energy range of photoexcitation by virtue of the different Fermi levels of ingredient the composite material. Few works suggest that the photocatalytic performance based on zinc oxide TiO2 composite nanofiber towards the decomposition of rhodamine B exhibited the most efficient photocatalytic activity in contrast to other ZNO TiO2 composite fibers, TiO2 particles and pristine TiO2 nanofibers. The enhanced photocatalytic performance has been illustrated in the figure as follows. Upon light activation, the electron transfer from the conduction band of ZNO to the TiO2 to that of TiO2. Simultaneously, the whole transfer from the valence band of TiO2 to that of zinc oxide. Thus, the efficient charge separation increased the lifetime of charge carrier and reduces the recombination of the electron-hole pair in the composite nanofibers, resulting in increased the quantum efficiency. Loading noble metal like gold, platinum or silver on the surface of semiconductor can also improve the photocatalytic activity, which can reduce the recombination of the photo-generated electron-hole pair and lengthen the photo-generated electron-hole pair lifetime through the conduction band electron trapping. It has been observed that the optimal photocatalytic activity of silver ZNO nanofibril could exceed that of pure ZNO nanofibers by a factor of more than 25, and the photocatalytic activity of the composite can be tuned by adjusting the silver content. I want to discuss the application of this electrospun nanofiber as chemical sensor. Chemical sensing is another field in which electrospun nanofiber are potentially being used. One-dimensional nanofiber fabricated by electrospinning have a specific surface approximately 1 to 2 order of the magnitude larger than flat film, making them good candidate for sensing application. For example, humidity sensor. Humidity sensors are very important, driven by their practical application in environment monitoring, industrial process control, our daily life, and so on. Till known, many humidity sensors based on nanostructure materials has been successfully obtained for the large surface area of nanoscale structure. Excellent sensing performance could be attributed to the unique structure of electrospun nanofibers. For example, the large surface of the nanofibers make the absorption of the water molecule on the surface sample easily. One-dimensional continuous structures of the fiber can facilitate fast mass transfer of the water molecule to and from the interaction region, as well as improve the rate for charge carrier to traverse the barrier induced by molecular recognition along the fiber. In contrast to traditional 2D nanoscale films, the interfacial area between the active sensing region of the nanofiber and the underlying substrate is greatly reduced. This advantage results in a significant gain in sensing signal and good stability. Due to such fabulous property of electrospun fiber, diverse ultra-sensitive humidity nanosensors have been developed based on electrospun nanofiber, including pristine metal oxide fibers, basic metal salt-doped metal oxide fibers, coupled metal oxide fibers, and conducting polymer fibers. Gas sensor is another example of chemical sensing through electrospun fiber. Gas sensor is a special device to detect the presence of different gases. Gained special attention for monitoring environmental pollution. Usually, gas sensing performance features such as sensitivity, selectivity, response and recovery, stability, durability, reproducibility, and reversibility are influenced by the intrinsic property of sensing material used. Till now, many attempts has been carried out to prepare gas sensor based on electrospun nanofiber membranes, including acoustic wave resistive, photoelectric, and optical gas sensor. I will discuss the electrospun nanofiber in lithium-ion batteries. Among diverse energy storage devices, rechargeable lithium-ion batteries with high energy density, long cycle life, flexible design, low self-discharge, high operating voltage and low memory effect are regarded as the effective solution to the ever increasing demand for high energy density electrochemical power sources. Schematic of lithium ion battery consisting of anode and cathode separated by one electrolyte containing dissociated lithium salt has been shown in the figure. Typical lithium ion battery consists of an anode and a cathode separated by an electrolyte containing dissociated lithium salt, enabling the transfer of lithium ions between the two electrodes. Usually, the electrolyte membrane is a porous separator film to prevent the physical contact between the anode and cathode. As the battery is being charged, external electrical power source inject electrons into the anode. Simultaneously, the cathode give up some of its lithium ion, which move through the electrolyte to the anode and remains there. Thus, the electricity is stored in the battery in the form of chemical energy. As the battery is discharging, the lithium ion move back across the electrolyte to the cathode, releasing the electron to the outer circuit for external electric work. In principle, normal power material have a long diffusion path for lithium ion and so electrode reaction kinetics, which reduce their practical application. Electrospun nanofiber gain a special attention in fabricating electrodes with lithium ion battery, driven by the shorter diffusion path in contrast to the commonly employed powder material. Fast intercalation kinetics for the large surface to volume ratio and decreased charge transfer resistance at the interface between the electrolyte and the active electrode material for the large number of lithium insertion sites can be provided based on it. Furthermore, electrospun based separator within lithium-ion battery also attract immense attention to their small pore size and large porosity, which can increase the cell resistance. Now let us discuss the electrospun nanofibers in fuel cell. Similar to the lithium-ion battery, fuel cell also contains three parts: the cathode, anode, and electrolyte. In general, fuel cells are the device in which chemical energy from a fuel is converted into electrical in the presence of catalyst shown in figure. Hydrogen is the most common fuel, but hydrocarbons such as natural gas and alcohol like methanol are sometimes used in fuel cell. Fuel cells are different from batteries in that they require a constant source of fuel and oxygen to run, but they can produce electricity continually for as long these inputs are supplied. Fuel cells are mainly classified by type of electrolyte they used. For example, proton exchange membrane fuel cell, alkaline fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, and solid oxide fuel cell. This is all based on the name of the electrolyte. The schematic of typical fuel cell has been illustrated in the figure, and it consists of anode, cathode separated by electrolyte. Recently, electrospinning technique has been introduced into the fuel cell for fabrication high efficient catalyst and proton exchange membrane. In principle, electrospun nanofibers based catalyst and the proton exchange membrane offers the good opportunity for high efficient fuel cell driven by their large surface to volume rate and controlled diversity in compositions. I will discuss the electrospun nanofiber for biosensing. Electrospun products gain special attention for sensitive detection of clinical, environmental, and food safety analytes driven by their extremely large surface area for providing a number of binding sites available for biological recognition, element immobilization, and diverse functionalization. Currently, the electrospun nanofiber, nanowire, and nanotubes are frequently investigated for use in biosensor. For example, it has been observed that polyvinyl alcohol nanofiber containing acetylcholinesterase, which is an enzyme, by electrospinning melt of PBA, ACHE, and bovine serum albumin BSA as an enzyme stabilizer. Recently, the incorporation of molecularly imprinted polymer within nanofiber network to construct high sensitivity analytical system has also been developed. So this way lot of applications might come in the application of biosensor. I want to discuss the electrospun nanofiber for water treatment. Heavy metal ion adsorption is one of the serious biological problem in aquatic system. Adsorption and filtration are the commonly used method for removal of these heavy metal contaminants. Recently, electrospun silk nanofiber mat have been applied in removing heavy metal ions. Higher adsorption capacity of around 2 mg per gram was obtained based on electrospun nanofiber mats in contrast to that of 0.7 mg per gram of the conventional material like wool silver for larger surface area of fiber mat. In addition to those polymetric nanofiber mats, metal oxide nanofiber mats have also been applied in heavy metal absorption. Let us talk the absorption of organic compound. Organic materials in drinking water can pose health hazards and also need to be removed. Many scientists explored the removal of phenolphthalein as a model organic molecule from water using PMMA, polymethylene methacrylate nanofiber membrane, functionalized with a very complex molecule named as phenyl carbamylated and azotophenyl carbamylated B-cyclodexatrine. The results obtained shown that the functionalized nanofibers membrane were able to effectively capture these PHP molecules. Metal oxide fibers mat also exhibits good ability in organic compound removal from water for its filtration and photocatalytic ability. Chan and Soon used titanium dioxide nanofiber mat to remove humic acid in water. In this study, TiO2 nanowire membrane achieved nearly 193% removal rate of humic acid with total organic carbon, respectively, via a co-current filtration and photocatalytic oxidation. The titanium nanowire membrane also showed an excellent anti-fouling ability owing to photodegradation of pollutants by the TiO2 nanowire membrane. So student, let us now summarize what we have learned in this module. We have learned that the use of one-dimensional polymer nanofibers as reinforcement agent to strengthen the base matrix. Application of nanofiber for filtration of bacteria. Metal-doped polymer nanofibers could be applied as a catalyst. The application of nanofiber as a photocatalysis. Nanofiber could be used for chemical sensors, humidity sensor, gas sensor. Nanofiber could be used for anode, cathode and separated material in lithium-ion battery as well as fuel cell. Nanofiber have been potentially used in biosensing owing to its unique properties. Contaminated water could be treated using nanofiber. Thank you very much.